Chapter 8, Hypothesis Testing. Alright, so to recap, we've looked at z-scores and found the probability that corresponded with less than or more than a z-score. We looked at sampling distributions and how they make the central limit theorem work. We looked at assessing normality by looking at QQ plots, and we started discussing the t-distribution. Chapter 8, I'm going to do things a little bit out of order because the book introduces things in a way that I think is a bit confusing. So watch this PowerPoint and then read through the book. We're skipping Chapter 5 entirely, and then we'll touch in different parts of Chapter 7 in different weeks of class, and later on in this PowerPoint, in a separate PowerPoint for this week. Okay, so hypothesis testing. If you think about a criminal court, if a person is accused of a crime, they are considered innocent until proven guilty. Similarly, in a research study, we have to prove that there was a treatment effect, but we start with the notion that there was no effect. So the test begins with the null hypothesis, meaning none or zero or not null, and is denoted by H sub 0, stating that there is no treatment effect. For example, there is no crime, the accused person is assumed to be innocent until proven guilty. So it's on the researcher. The research study gathers evidence to show that the treatment actually does have an effect, just like the prosecution collects and presents all available evidence in an attempt to contradict the innocent hypothesis and hence obtain a conviction. Note that in both scenarios, the researcher and prosecutor are trying to prove that the null is false. If there's enough evidence, the researcher will conclude that there is a treatment effect, or they, what we call, reject the null hypothesis in favor of the alternate hypothesis, which is denoted H sub A, or in the book, they do sometimes, you'll see sometimes it's H sub 1, that there is an effect. Just like if there's enough evidence, the court will reject the innocence hypothesis and determine that the defendant is guilty. If there's not enough evidence of an effect, the researcher will fail to reject the null, just like the research, note that the researcher doesn't conclude that there is no effect, just that there isn't enough evidence to prove that there is an effect. Similarly, the prosecution does not present enough evidence to prove the defendant guilty, the court will find him not guilty. Notice that this does not prove him innocent, but merely that there was not enough evidence to conclude the defendant guilty. So hypothesis testing is very similar to the court system in that you're trying to prove that there is a treatment effect, that there's enough evidence to reject the null hypothesis, which states that there's no effect. Just like in the court, you can't say, yeah, okay, we didn't have enough evidence to prove him guilty, so he's innocent. We say, no, we didn't have enough evidence to prove him guilty, so he's not guilty. Alright, so this is the beginning of inferential statistics. A hypothesis is a claim or a statement about a property of a population. So remember that when we measure population, we call them parameters, and we use those Greek letters for them. So our hypotheses are written in terms of parameters, and we use the Greek letter. A hypothesis test is a statistical method that uses sample data to evaluate a hypothesis about a population. The general goal of a hypothesis test is to rule out chance, which is also known as sampling error, as a plausible explanation for the results from a research study. In the book, I think there's 7 steps, but I'm going to boil it down to 4. So the first one is we state the hypothesis about the population. Then we set the alpha level. And it's usually alpha is equal to 0.05. Now I know alpha is a Greek letter, but in this situation, this is not a parameter. This is just a name given to the significance level. And so we want it to be 0.05. Then you're going to calculate your test statistic, and then we're going to draw our conclusion. Individuals in the sample are noticeably different from the individuals in the original population. We have evidence of the treatment, that the treatment has an effect. Now this is the key word, noticeably different. However, it's also possible that the difference between the sample and the population is simply sampling error. So we want to make sure that it's noticeably different. And I'm going to show you. So the first step is to state the hypothesis about the unknown population. So the null hypothesis, H sub 0, states that there is no change in the general population before and after an intervention. In the context of an experiment, H sub 0 predicts, or the null predicts, that the independent variable had no effect on the dependent variable. I like to think of it as nothing is happening here. There's no difference. The alternate hypothesis, which is denoted H sub A or H sub 1, states that there is a change in the general population following an intervention or a treatment or whatever. In the context of an experiment, it predicts that the independent variable did have an effect on the dependent variable. So in the book, they go into section 8.2 and they do proportions. And I think this is out of place, so we'll do this at the end, but I just want to show you that population proportion is denoted as P. And then this P, I couldn't get this hat to be right over the P, but close enough. The sample proportion is called P hat. And it's not to be confused with the p-value, which we'll talk about in a few minutes. So the sample size times the success is the number of successes, is the probability of successes. So the sample size times the proportion of successes in the null hypothesis. And then NQ is equal to the failures. The sample size times the proportion of failures, which is 1 minus the successes. And we'll get to this at the end. I just wanted to show you this in order. All right, so let's go to an example. A formal hypothesis test is to be conducted using the claim that the mean height of men is 174.1 centimeters. So what is the null? Remember that there is no effect or nothing is happening here, or what we know is what is being said that we know. So the null hypothesis is just that the mean, and here we use mu because we're talking about the population mean, is equal to 174.1. The alternate hypothesis is that there is something happening here, or what we know is different than what we said is being known, or what is said we know. Sorry. Here we aren't saying there is more or less, we're just saying it's just not 174.1. So we use this not equal sign. So our alternate hypothesis is H sub 1 or H sub A, and then you do a colon, we say mu is not equal to 174. Null says it's 174, alternate says, you know what, it's not 174. But we can make other claims. What if we say that the mean height of men is more than 174? What is the null and what's the alternate? The null would be, same thing, null is mu is equal to 174.1. The alternate is that mu is greater than 174.1. What if we say that the mean height of men is less than 174.1? What's the null? What's the alternate? The null is that it's the same thing, mu is equal to 174.1. Alternate is that mu is less than 174.1. All right, let's do another example. Here we are on page 351 from the homework problems. Most adults do not have hypertension. When 983 randomly selected adults were tested, it was found that 70.9% of them do not have hypertension. So let's express this claim in symbolic form. So the probability of those that do not have hypertension is more than 0.50. So we just said most adults don't have it, all right? So what this is, I'm saying it in symbolic, the probability of people who don't have it is more than half, because that's most, right? More than half. So what's the null? The probability is equal to 50.50, and the alternate is that the probability is greater than 0.50. We don't even have to deal with the fact that we found that 70.9 of them don't. We're just expressing this in symbolic form. All right, then we go on to step 2. We have the alpha level, which establishes a criterion or a cutoff for making a decision about the null. We can have alpha is equal to 0.01, or alpha is equal to 0.05, which is the one most used, and then alpha is equal to 0.001. And the critical region consists of outcomes that are very unlikely to occur if the null hypothesis is true. That is, the critical region is defined by sample means that are almost impossible to obtain if the treatment has no effect. Now I know this still sounds like crazy talk right now, so I'm going to just keep going and try to make it clearer. All right, in your mind, overlay a normal curve here. All right, we know that the mean of a normal curve is 0 with a standard deviation of plus or minus 1, plus or minus 2, right? 95% of the people will be within 2 standard deviations, right? 95% of whatever we're looking for, IQ, average heart rate, whatever. We'd have 0.025% and 0.025% over here, meaning add those together and you get 0.05%. So remember we said the area under the curve when we were doing all those z-scores is equal to probability. Same thing works here. So if I put 0.025% of the probability here and 0.025% of the probability here, add them, that's 0.05%, right? And so that's the same as our critical value, our alpha level. Similarly, I could put 95% here and put all 5% of the probability in this end, or I could put 95% here and put all 5% of my probability in this end. Hang in there with me. Let's just keep going, and hopefully it will make sense in a few minutes. All right, so remember, we said 68% are in the orange, 95% are within the dark orange and light orange, and then 2%, really 2.5% are in the yellow on either side, and you add them and you get 0.5%. So the whole point, if we go back to the beginning of this PowerPoint, we said that we want to be sure the null is saying that there's no effect from our treatment, our intervention, whatever we're looking at in our experiment. The null says, you know what, it didn't work, nothing happened. But we say in our alternate hypothesis, yes, it did work, something did happen. And we have to have enough evidence to show that it didn't happen by sampling error or by chance. And we have said arbitrarily, but we said, you know what, I can accept 95% of it would be due to chance. But if it's in that 5% chance, if it landed in that area, I'm going to accept that as enough evidence to prove him guilty or prove that we can reject the null hypothesis. And so what are the chances that the score occurring is small and the evidence should be found in either tail? Could be found in either tail. So we have a critical value. We said 2.5% of the probability here and 2.5% of the probability here. And I've just been rounding and saying plus or minus 2, but actually the z-score is at plus 1.96 and minus 1.96. So almost 2 standard deviations, but not quite. So if I find a z-score or a t-value that's like 3 or 4 or 5 or 15, if it's negative, it'd be way over here. If it's positive, it'd be way, way over here. And we would say, you know what, that's pretty good evidence that it didn't happen by chance. So we could look, this is where we could look at either tail, plus or minus, or we could look in just one tail. And I'm going to show you examples of when we're using a one-tail or a two-tail test. So a one-tail works pointed either way, so it could be to the right or it could be to the left, where the chance of that score occurring is small and the evidence can be found in one or the other of the tails. And here, instead of the critical value being 1.96, it's 1.645, because now it's not 0.025 plus 0.025. Now we have all 5% or 0.05 of the probability in one of the tails, and so that changes our z-score slightly. So now if I had a z-score of 1.7, I would be to the right of this critical, this cutoff value of 1.645, and I would say, yep, reject the null. Okay, so I can have a right tail test, which is over here in the right tail, or I can have a left tail test, which is over in the left tail value. So let's go back really quick. Remember when I said we could go, what if it's more than, what if it's less than? We're just going to follow the arrows. Let me get there. So if I say mu is equal to 1.741, and I say, you know what, men are actually taller than that, I think the average man is taller than that, I'm going to say it's greater than, I just follow the arrow and I know that it's a right tail test. Critical value is 0.1645, and the critical region is the alpha is equal to 0.05. We're not going to be calculating these. I'm going to show you in the PowerPoints, but after this we're just going to use SPSS and we're going to look at this value. I'll explain. Hang in there with me. Now if I want to say, you know what, I think men are actually shorter than that, I say the mean is actually less than 1.745, I follow the arrow, and now it's just negative 1.645, all the probabilities in my left tail, and now I have to score less than negative 1.645, so negative 1.75, negative 2, negative 3, any of that would be enough evidence to reject the null. Okay, but what if we don't know? Like that first one, we said, we don't really know if it's bigger or little, we just know that it's not. So I use this not equal sign, and it could be in either tail, and so we have to split the probability, okay, which is what I've been saying. All right, so then we do the hypothesis test step 3. So we compare the sample means, our data, with the null hypothesis. We went out, we sampled 100 people, we took their height, we did calculate the test statistic, and then we compare it against negative 1.96 or positive 1.96. So we compare the sample means with the null hypothesis, compute the test statistic, and see if it's bigger or smaller than the critical value, plus or minus 1.96 for the two-sided test, or plus or minus 1.645 for a one-sided test. But we can just let SPSS do this for us. The test statistic will be given to us. It forms a ratio comparing the obtained difference between the sample mean and the hypothesized mean versus the amount of difference we would expect without any treatment effect. Okay? Then we have to make a decision. If the test statistic results are in the critical region, so if they're way over here or way over here or either side, then we say, you know what, it's time to make our decision that, yeah, it is significant evidence that there is a treatment effect and that the treatment had a significant effect. In this case, we reject the null. If the mean difference is not in the critical region, we conclude that the evidence from the sample is not sufficient, and the decision is to fail to reject the null hypothesis. We never accept the alternate, we just either reject the null or fail to reject the null, or do not reject the null. Alright, so let's look at the z-score statistic. The term test statistic simply indicates that the sample data are converted into a single specific statistic that is used to test the hypothesis. This is called a point estimate. Later we'll be talking about confidence intervals, not in the book. A random sample is selected from a normal population with a mean of 30, mu of 30, and a standard deviation of 8. And this is from a population. After a treatment is administered to the individuals in the sample mean is found to be mean m is equal to 33. If the sample consists of 16 subjects, is the sample mean sufficient to conclude that the treatment has a significant effect? Use a two-tailed test with alpha is equal to 0.05. So step 1 is to state your hypotheses. So the null hypothesis is that mu is equal to 30, and the alternate is just that mu is not equal to 30. So we have a two-tailed test, right? We're not saying it's bigger or smaller, we're just saying it's not, because I said use a two-tailed test. Step 2 is set the alpha level, and we've already been told use an alpha of 0.05. And I'm always going to tell you to use 0.05 just to be consistent. Alpha is equal to 0.05. Okay, so step 3 is to calculate the test statistic. And I'm showing you this, but we're not going to ever do this by hand. We're just going to look at the p-value, but I want to show you where it comes from. So remember how I said we were using t-distributions when we use a sample? Because our sample size is small, it's only 16 people, we have to use the t-distribution. So I'll show you how that's done, and then going forward, we're just going to use the p-value. All right, so the mean was 33 minus the hypothesized mean, which is 30. Our standard deviation was 8. Our sample size was 16. So we get 3 over 8 divided by 4, so 3 over 2, which is 1.5, right? So we come over here and we see that 1.5 is about here. Now, we're using a t-distribution instead of a z-distribution because we're using a sample, so we have to go on the inside cover of the textbook, on the back. We have the negative and the positive z values. You turn one more page in and you get to the t table. So then we have to make our decision. Since the test statistic is smaller than the critical value, so if I look in the table, I see that we need to be bigger than 2.131 or smaller than negative 2.131 from the t-table, and we got a 1.5. We're here. We're not in the region of rejection, so we fail to reject the null hypothesis. And then we make our sentence to summarize. There is not significant or sufficient evidence to support that the treatment effect causes a significant effect, or in this case, there is not sorry, it's hard to say all these S's. There is not sufficient evidence to support the claim that men's height is not 1.74 or 174.1 centimeters. Okay, so more about hypothesis test. A result is said to be significant or statistically significant if it is very unlikely to occur when the null hypothesis is true. That is, the result is sufficient enough to reject the null hypothesis. Thus, a treatment has a significant effect if the decision from the hypothesis test is to reject the null hypothesis. But I keep talking about a p-value. So, the p-value is the probability of getting a value from the test statistic that is at least as extreme as that test statistic obtained from the sample data, assuming that the null hypothesis is true, which I find very confusing. So I'm going to say it again. What this means is that if there were no effect, that is, the null is true, would we find a test statistic in the extreme ends of a normal distribution? No. If the null is true, our test statistic would be in the big humpy part of the normal distribution, plus or minus to within the 95% probability of finding a test statistic between plus or minus 2 standard deviations, or 1.96, right? Most of the time we're going to find stuff in the middle part of a normal curve. When we find things that are at the ends, in the extremes, that's when we will reject the null. So what we're going to do is forget all of this calculation business, because that becomes incredibly confusing, and it's fine when you have 16 people in your data set, but when you have 500, you don't want to do that by hand, and that's why we have computers now. There's no sense in teaching you how to do it by hand when we have a computer that we're going to use going forward. Might as well teach you how to do it now. So with SPSS, we're just going to look at the p-value, which they call sig, because everybody likes to make things confusing. The p-value is called sig, which means significance, and so we're just going to look for the sig. That is, if the p-value is less than 0.05, then we conclude that the null is false, and we can reject the null hypothesis. So, we won't be calculating our own experimental data by drawing normal curves and calculating all this by hand. We're going to use software in order to do it. In section 8.3, page 376, number 21, lead in medicine. Listed below are lead concentrations measured in different Ayurvedic medicines. The lead concentrations are listed for meds made in the USA. Use alpha is equal to 0.05 to test the claim that the lead concentrations in all Ayurvedic medicines made in the USA are less than 14. So we're going to use our raw data, which is given to us, and we're going to say our null hypothesis is that the mu is 14 and that the alternate is less than 14. State the critical value. This was done for us. They just said alpha is equal to 0.05, so we're going to consider the p-value. So even though this indicates a one-tailed test to the left, we're still looking at the sig, or p-value in SPSS output. Okay? We're just going to be looking for less than 0.05. So we go in and we enter those data into SPSS, right? I can go and change the name to lead level in the variable view. Now we're ready to calculate the test statistic. We are now going to do our first t-test for the one sample case. We have one sample, and we're just comparing it to a hypothesized mean. What this means is we are testing a mean from a sample against a hypothesized population mean. Our null hypothesis is that the population is 14 micrograms. Our alternate hypothesis is that it is less than this. All right, so it's a left-tailed test. You go to Analyze, Compare, so you go Analyze, slide down to Compare Means, slide over to One Sample T-Test. I bring, my variable would be here, lead level, over into the test box, and then I change it to 14 because that's what we specified in the alternate hypothesis. I click OK, and it gives me this summary table, which just gives us the mean and the standard deviation. So the mean of our sample was 11, and that's less than 14. So the first table shows us that the sample mean is definitely less than 14. It's 11.1, and our standard deviation is 6.5. And then we look, so our mean is 11.05. Our t-value is negative 1.4. So these read the same as z-values. It's negative 1.44. We know that a z-value of plus or minus 1.645 for a one-way z-test is required. But this is a sample and a small one, so we would use the t-values, but we don't have to. We're just going to look at the p-value. Our degrees of freedom is 9 because our sample size was 10. You take away 1 for the degrees of freedom. To make things confusing, SPSS likes to call the p-value sig, or in this case, sig two-tailed. Just look for the word sig, okay? And we see that it's 0.183. It is not significant because it's bigger than 0.05. If we look back at the book in table A3 for degrees of freedom 9 and at 8.05, we see that we need a t-value of bigger or less than 1.8, and this was only negative 1.4. So it's smaller, so we do not reject the null. If the p is low, the null must go. Just remember that. If the p is low, the null must go. The p was not low. It's not less than 0.05. I like to think of it as a nickel in your pocket, right? 5 cents. If it's less than 5 cents, if it's 1 penny, 2 pennies, 3 pennies, or 4 pennies, or no pennies, it's significant. But if it's a nickel or bigger, then it's not. Okay, so if the p is low, then the null must go. If the p is less than 0.05, then we reject the null hypothesis. If it is not, we fail to reject the null hypothesis. So in this case, we fail to reject. So if I run a test and my friend Gilbert runs a test, my p-value is p is equal to 0.01 and his p-value is equal to p to 0.04. Whose test is better or more significant? Let's think about that again. I only have 1 penny, he has 4 pennies. So mine is smaller. Is mine more significant than his? Mine, right? Because my p-value is smaller. Wrong. There are some concerns about hypothesis testing. We have to measure the effect size. So there are 2 serious limitations when using a hypothesis test to establish the significance of a treatment effect. When the null hypothesis is rejected, we are actually making a strong probability statement just about our sample data, not about the null hypothesis. Demonstrating a significant treatment effect does not necessarily indicate a substantial treatment effect. What we will do is we're going to calculate the magnitude of the effect by using an effect size. We'll calculate this from our output. So a measure of effect size is intended to provide a measurement of the absolute magnitude of a treatment effect independent of the size of the sample being used. And the first one we're going to learn about is this guy called Cohen. Cohen's D. And it measures the size of the mean difference in terms of the standard deviation. So a small effect is considered a d-value of 0.2, 0.5 is a medium effect, and 0.8 is a large effect. These are totally randomly decided by this guy named Cohen, but it's the convention that's been used ever since. And so if you calculate, say, a d of 0.3, you would say it's a small to medium effect, or a 0.7 is a medium to large effect. And then you just provide a citation with Cohen, probably 1988, I think is the paper I always use, and keep on trucking. All right, so how do I calculate this? I just take the mean difference, which is given to me in my output here, and I divide it by the standard deviation, which is here, and I get 2.95 divided by 6.46. I don't worry about the negatives or the positives, it's just absolute value, and I get 0.046. Since this wasn't a significant test, this is very small, not surprising. Okay, and now back to proportions. Back to that one on page 360. In testing a method of gender selection, 10 randomly selected couples are treated with the method, some method of gender selection. They each have a baby, and 9 of the babies are girls. Using an alpha of 0.05 to test the probability of having a baby girl is greater than 0.75. Now, I'm showing you this as a separate slide because the way you do proportions is different than what I just showed you with the one sample test. Proportions are different, and I'll show you in SPSS. So our null is that the probability of having a girl is 0.75, and the alternate is the probability of having a girl is actually greater than 0.75. So we had 9 successes out of 10 trials, so we already know it was 90% successful. But let's look at SPSS, and it's kind of busy. I see that this slide is very busy, but it's not often that you'll probably do this, but if you have to, it's very simple to do. So I go in and I code my girls as 1 and my boys as 2. I got 9 girls and 1 boy, okay? So I do my value labels and I've done that. Then I go to Analyze, I go to Non-Parametric Tests, I go to Legacy Dialogues, and I go to Binomial. I click there, and it brings it up. And it's very similar to the one sample test. You'll have that one variable, which I call gender, bring it over, and I'm testing the proportion now of 0.075. But I'm giving it a cut point of 1 because these are 1s and this is 2. So anything that's not 1, they're going to test against 1. So my cut point is 1, so it's testing the girls against the boys. I could have done it the other way and it would have done the same thing. I could have said 2, and it would have tested the 2s against the 1s. All right, so group 1 is less than or equal to 1, and group 2 is greater than 1. And my test proportion is that it's 0.75, and I have a SIG two-tailed test, and this is not significant. What it's saying is that it is not 0.75. Okay, we have learned that in order to test where there was a significant finding of a study, not due to chance, we have to do hypothesis testing. We have 4 steps in a hypothesis test, and once we get to the end, based on our findings, there needs to be a conclusion or a decision made. I'm going to cover now in a short PowerPoint on confidence intervals, type 1 and type 2 errors, and power.